Alright guys, welcome to the channel. We're going to be solving a question about 2D moment, and in this one we need to calculate the moment of the 200 Newton force about point A by using 3 scalar methods and 1 vector method. So we're going to use 4 different methods in order to solve this question. 3 scalar and 1 vector method. So we know that for finding the moment, so here we are trying to find the moment about point A. And since moment is a vector, we have the cross product of r and f, which r is distance vector and f is the force that we have in here. So let's go with the 3 scalar methods first. And after that, we're going to go by the vector method, which is what we have in here. So since we have a 2D question, we're going to use the 2D shortcut that we discussed in the channel over and over. We basically have the x and y in the question, so we're going to break down the force into x and y components. So if we do that, this will be the x component, which is negative, and we have a positive. And y force 2, the x would be minus 200 cosine of 15, and the negative sign is, again, because it's to the left, and 200 sine of 15 would be the y component. So let's go with the first scalar method. So we're trying to find a moment about point A. We're going to call counterclockwise positive as always. So we have the moment of the x component, which is the 200 cosine of 15. As we can see, the moment is in this direction about point A, so counterclockwise positive. So 200 cosine of 15 degrees, and we have the moment of y. If you look at it, we'll see that the y is also making a moment in this direction, so another counterclockwise. Sorry, before going to that, we forgot to put the r in here. So that was the force, and the distance that we have is the vertical distance to the line of action, which is the 280 millimeter. We're going to divide it by 1,000 in order to get it in meter. And the force is obviously Newton. So that was the x component, and they have 200 sine of 15 degrees, and the distance that we have, this is the line of action of the force, or I should say the y component of the force, and the vertical distance would be what we have from here to here, 400 divided by 1,000, and you just have to add these two. And again, we're dividing by 1,000 in order to get it in meter. Let's calculate this. So 200 cosine of 15 times 280 divided by 1,000 is 0.28 plus 200 sine of 15 this time. I put it here. So this has to be cosine of 15. So 200 sine of 15 times 400 divided by 1,000, 0.4, and that's going to give us 74.79, or we can round it up to 74.8. Again, the force is in Newton and the distance is in meters, so Newton. That's the first scalar method. Let's go to the second method, see how we can find this. So if we look at this figure in here, we have these two angles same as each other, both 15 degrees. And another way to find the moments is that we know that moment is, so actually I wrote it in here, r cross f, which is rf sine of, let's call it alpha, which alpha is the angle between r and f. And when we have the alpha 90 degrees, the sine of 90 degrees would be 1. So basically we have r times f. But we have to find the vertical or perpendicular distance from the point that we are trying to moment about, which is A. to the line of action of the force, which is what we can see here, the red force. And basically, the distance that we have to figure out the AE in here, which is the perpendicular distance to the line of action. That way we have that 90 degrees for alpha. So we should be good to go by multiplying just F and R. So we have to figure out how we can find AE. And if we do that, our moment is pretty easy. Counterclockwise positive. As we can see, the force about A is going to make a counterclockwise moment. So it is positive. So we'll be positive 200 times the AE, which we have to figure out how we can find it. So let's see how we can find AE though in here. So if I draw a line in here perpendicular to this, we know the side of this yellow rectangle is 280 millimeter, and we know this angle is 15 degrees. So if we want to find this, we have 280 cosine of 15 degrees. So basically we have 280 cosine of 15 degrees. You can divide by 1,000 in order to get it in meter 2 plus this part, which I'm going to show how we can find that. So if we draw a parallel line to AE in here, we're going to have a rectangle in this. And if we look at this right triangle that I'm highlighting in green, so this one, we know that angle is 15 degrees. So if we want to find the perpendicular side, this one or this one, they are the same. And we know this side of the yellow triangle is 400 millimeter. We basically have 400 times sine of 15 degrees, and we're going to divide it by 1,000. And that way we have the whole distance AE. So let's calculate what's that going to be. So 280 times cosine of 15 plus 400 sine of 15. And we're going to divide that by 1,000 in order to get it in meters. So 0.374 meter. So now we have AE. Our moment would be basically force, which is 200 Newton times AE, 0.374. Let's multiply this by 200, see if we get the same thing. Yeah, we get the same answer, 74.8 Newton. So that was the second method. And I'm just going to clean up the figure. So the third method, if we can dissolve the force 200 at point C into these two components, which we are allowed to do this. So basically our R would be any line that connects the point that we are trying to find a moment about to the line of action. So we can literally pick any of these. So if this is the line of action of the force, we are allowed to any of these R's to solve the question. That's the main takeaway of this question. Actually, we are trying to take different R's, but obviously we are going with the one that is easiest for us. The 2D shortcut or the first method that we tried is gonna work in all cases. But yeah, sometimes in this question we can find AE2, or we can actually go with point C, which is the third method. As long as we are not asked to pick different methods, we can go with any of these. So let's try the R this time. So we are trying again to find a moment about point A. And our R in here would be our AC, which, as we can see, the vertical component is going to pass through A. So basically it won't make any moment, and we only have the moment of the X component. Again, this is 15 degrees, which was 200 cosine of 15 degrees. We have a positive sign, same reason the moment is counterclockwise. And we have to figure out the distance of AC. So our moment in here is basically 200 cosine of 15 degrees times AC. Let's see how we can find AC. So AC is basically AD plus CD. We already know AD, it's 280 millimeter. We're going to divide by 1,000 to get it in meter, plus what we have for CD. And if you look at this right triangle that I'm highlighting in green, this one, if you want to find the tangent of 15, we basically have the opposite CD, which is what we are looking for in here, over the adjacent 400. So basically CD is 400 times tangent of 15 degrees over 1000. So we should be able to find the AC pretty easy. 400 tangent of 15 plus 280, and we're going to divide that by 1000, and we're going to divide that by 1000, 0.387 meter. So our MA was basically from the first line plus 200 cosine of 15 degrees times 0.387. Let's see if we get the same answer. So basically have that times 200 cosine of 15. Cosine of 15. And yeah, we got the same answer, 74.8 Newton meter. And that would be our third method. And the last one is what we have in here, the definition of the moment. And going by the vector, so if you want to find, we have basically R, or the cross product of R and F. And we have to figure out our R and F in a vector form. Let's go with each of them. So R, as I mentioned, we can go basically with any of these R's that I showed in red. But let's just pick one of them. Let's go with this one. We can call it RAB. Or the other way of showing it is RB with respect to A. So basically we are going 400 meter in X direction and 280 millimeter in Y direction. So our R is basically 400 millimeter divided by 1000.4 I, and we're gonna go 0.28 in Y direction. Our F in here, we already found it, is minus 200 cosine of 15 degrees in X direction and plus 200 sine of 15 degrees in J. So now we have our cross product in here, which means we have to find the determinant of these matrix. The second row is always the distance vector, so 0.4, 0.280 minus 200 cosine of 15, and our J is 200 sine of 15, and we don't have any K, and we have to find the value of this determinant. So for I component, so we know we're going to get a vector at the end of this, meaning we have, well, again, meaning the cross product would be in a vector form with ijk, but in here, if we look at the determinant, the I component, since we have the cross multiplication of these two, will be 0, and we have the same thing for j. If we cover the j, we have the cross multiplication of x and z, again 0, but we only have z component in here, which is going to be cross multiplication of these two, so 400 times 200 sine of 15 degrees minus 0.28 times minus 200 cosine of 15 degrees, which these two, the two negative signs will be positive, and we're going to get basically what we have in the first method, or what we had in here, which is going to give us 74.8 Newton meter, and the direction would be in K. And keep in mind that we're going to get a vector at the end of the answer. So yeah, that's pretty much it. It's a very good recap for the definition of the moment in different ways. And as I mentioned, the biggest takeaway is our position vector, which is basically any vector that connects point A to the line of action of the force. As long as we are not limited to use any of them, we usually go with the easiest one. Here, point B is a good point. As long as we can find the AE easy, we won't be dealing with any force with cosine of 15 or sine of 15. So just have the value of the force 200 times the distance vector. And yeah, let me know if you guys have any questions. Hope everything was clear, and you guys take care. I'll see you in the next one.